There it goes. Yeah, so we're very happy to have Eric to give his last lecture. You'll have an opportunity to ask him many more questions tomorrow during the Q&A session. But yeah, take it away, Eric.
Great. Thanks, Tom. Before proceeding, everybody can see the screen. So
yes.
Okay, thanks. So yes, the last lecture of my series, at least. And so the first three were about general dimensions, and as you can see, this last one will be about the special realm of ADS3 CFT2. Tomorrow at the Q&A or on Slack, whenever, if you have questions about any dimension, feel free to ask. So we're not going to talk about higher dimensions explicitly today, although I won't refuse questions, but you'll have ample opportunity to ask about the past three lectures elsewhere. So don't worry if you had some lingering questions. That said, if there are any really lingering questions, let me just ask now if anyone had anything they wanted to ask before we really get started. Okay. So yesterday was asked whether we could imagine having a gap in the spectrum of a large C strongly coupled CFT, not up to some scale delta gap representing the higher spin single trace gap, but up to order C, which in the bulk would be some power of the Planck scale. And this would be a kind of M-theoretic situation where you don't have another scale besides the Planck scale, and we would want to ask, can we make a theory extremely sparse? So let's see. Gap to order C. Some M-theory compactification one might imagine. And so this question finds a natural home in ADS3 CFT2. Natural question. CFT2, where answering it has indeed been a driving force behind lots of work for several years. And so there are a few reasons why this is an actual question to ask in the context of ADS3 CFT2. And so let me just name a few of them. So this is by way of sort of motivating this whole subject somewhat philosophically. So the first comment is that every theory of 3D gravity has ATZ black holes. Now, just when I say 3D gravity, I mean with ADS3 boundary conditions. So that's just a habit of working in this field for long enough, but that's what I mean when I say 3D gravity today with negative cosmological constant. And so this point is worth emphasizing because, well, first of all, besides being true, it's in contrast to the situation in higher dimensions, where in contrast, not every theory of greater than 3 gravity has, say, ADS Schwarzschild solutions. For example, the Vasiliev theory does not admit an ADS Schwarzschild black hole solution. Of course, Einstein theory does, but the existence of that solution is tied to the fact that one is working with this universal two derivative action. And the situation, though, in 3D is different. Any theory of ADS3 gravity has ATZ black holes. And the lightest ATZ black hole has mass greater than equal to 0. And when we recall that the mass of empty ADS is equal to -1 over 8g, this translates into, well, delta equals 0 on the CFT side, it's the vacuum state. And this translates into delta equals C over 12, where I'm using the fact that C equals 3 over 2g. So there are these universal states at this particular value, delta equals C over 12. And so there's something to shoot for. Can you show that there's a gap that goes up to C over 12? Okay. Seems like it is a natural place, an upper bound on what the gap could be. But at least there's some universal idea of what the gap might be in the most sparse case. The second point is that 3D gravity is perturbatively normalizable. And this is equivalent to the statement that it can be formulated perturbatively. 3D gravity is perturbatively a topological gauge theory. Now, eloquently talked about these points. And likewise, there are only boundary gravitons in NDS3. There are no local degrees of freedom. These are all the same point. Okay, but in the bulk, the theory seems quite a bit more tractable than the usual dynamical gravity in higher dimensions that we're used to. And finally, 3D gravity cannot couple linearly to matter. By linearly, I mean linearly in matter. So how do we know this? Well, the asymptotic symmetry group of 3D gravity is the Virasoro algebra, and that's a closed algebra. So in CFT terms, what this means is that the stress tensor dynamics are a closed subsector. And so in particular, if you take, say, a 3-point function of 2 stress tensors and some other operator O, which is not comprised of stress tensors, then this is identically 0. Okay. In higher dimensions, this is not true. And yesterday we talked about some examples of such couplings being non-zero. So like d greater than 2 CFT. So what this means is that adding matter to a theory of gravity in ADS3 has no effect on the purely gravitational dynamics. And so in this sense, the interplay between the matter and the gravity seems milder. And for this reason, and for the previous reason number 2, it seems like there's a chance that a theory of pure gravity could exist. So those are some reasons why a gap to the Planck scale seems possible in 3D gravity, certainly much more so than in higher dimensions. Now, on the CFT side, what extra structure is there in 2 dimensions that we don't have in higher dimensions? Well, you already know the answer. There are 2 that I will highlight. The first is that there is the Virasoro algebra, which is a local symmetry. Let me write this algebra, not because you don't know it, but because I can't get enough of it. And in particular, the fact that it's so simple, and yet there's so much rich physics that comes out of the algebra, and in particular, its representations. So there it is. That's it, right? That's it. But there's still so much we don't know about the consequences of Virasoro symmetry for 2D CFTs, on the representations that can be furnished in a consistent theory, and how best to write some of the universal features of 2D CFTs that follow from this. It's kind of surprising, to be honest, and it's, I think, inspiring. I try to work on higher dimensional CFT, and I do, but then 2D tends to sort of pull me back because there's a lot to do, and sometimes you think, oh yeah, it's not, a lot's been done, you know, but then someone writes a great paper, and then you realize how much more there is to do, and how many tools you have. Okay, and this is one of them. The second one, the second simplification of 2D CFTs compared to higher dimensions that you also know about is modular invariance of local observables on the torus, such as the partition function, or more generally, modular covariance of local correlation functions in the torus. And so, okay, let's just write this out once quickly. What is the statement of modular invariance? Well, for the partition function z, it's a statement that under SL2Z transformations of tau and tau bar, the partition function is invariant. And so this relates low and high energy states. Just schematically write this. This is the essence behind the Cardy formula, which uses the fact that if you look in the regime tau goes to I infinity, where Z is dominated by the vacuum state, then modular invariance, in particular the S transformation, maps this to tau goes to 0, where Z is dominated by a high energy tail, because in the expansion and powers of Q, which is either 2 pi I tau, well, tau is going to 0, so that's going to 1. So high energy states count a lot. Whereas in the first expansion, they count a little, but the two are supposed to be identified with each other. So high energy and low energies are intimately related, much more explicitly than in higher dimensions. For later use, let's write, I'm going to sometimes write Z of tau. I don't mean this is holomorphic. I just don't want to write tau comma tau bar all the time. If this gets confusing, I'll stop, and I probably will even confuse myself at some point. So just if you want me to do otherwise, feel free to put in a request. So it is useful to write this in a character expansion. Where these characters are given as follows. Well, let's define the generic character first. If I have a state of left moving dimension H and right moving dimension H bar, then the character is given by the following formula. And the vacuum character is almost the same as just plugging in HH equals H bar equals 0, but then there are some null states due to the SL2 invariance of the ground state. And the theory-dependent information here are these degeneracies D. So one idea that we're going to talk about today at some length is the idea of what's called the modular bootstrap. Which is really the major 2D bootstrap effort over the past many years, which originally is due to Simi and Hallerman in a paper in 2009, and has been significantly developed since. What this does is it tries to harness modular invariance to make sharp statements about things like spectral gaps. It's exactly analogous to trying to use crossing symmetry on 4-point functions to extract statements about spectral gaps or OP gaps. And actually, the problem of using modular invariance in a bootstrap way can literally be mapped to the use of crossing symmetry for 4-point functions in a way which I won't explain. But if you think of this S transformation as analogous to mapping Z to 1 minus Z in a 4-point function where Z is the cross ratio. So part of the goal of today will be to talk about the modular bootstrap results and how close we are to trying to prove whether this is really possible. The upshot is that we have definitely not proven that this is possible. This is very much still a work in progress. And in my opinion, it's open as to what the optimal gap should even be expected to be. And I'll also talk about some other universalities in 2D CFT that aren't strictly modular bootstrap, and some, I think, deeply important open questions about which we really have no idea. So the idea of today is to expose you to some of what's been done, but as with all my lectures, trying to really emphasize the questions that are open so that you can read about them and hopefully think about them yourself. So are there any questions to this point.
Can I ask a question about the equivalence to Chern-Simons theory?
Yeah.
Well, why do we believe that it's not true non-perturbatively? You said it's true perturbatively, but
I think Alex talks about this a little bit in his lectures, but there are a few reasons. The first has to do with the way different topologies are treated in the path integral. The second has to do with the fact that there are, well, admissible connections that one would integrate over in the Chern-Simons formulation, which when translated back to metric language correspond to degenerate singular metrics, which in a metric frame of mind, one would typically not want to include. Those are two of the reasons that are usually cited. But I think that, yeah, those are the two main reasons that come to mind.
okay, thanks.
Sure. Any other questions? Okay. Before talking about the modular bootstrap and what we can expect on the spectral gap question, let me just emphasize two more things. So I guess this is still sort of in the sort of introductory segment. So despite all these things, that these handles we have on constraining the space of CFT2, there are definitely things about ADS3 CFT2 that are not simpler than in higher dimensions. So if you want to compute Witten diagrams for some light fields, calculationally that proceeds the same way as in higher dimensions. There are observables that depend on the higher spin gap in a large C theory with a separate higher spin gap scale. And that dependence is not particularly simpler in general, nor is it simpler to compute. So for example, you can't compute the interpolation between weak and strong coupling of some function of delta gap any better than you can in higher dimensions. That's still an inherently strongly coupled problem. And it's a problem that is not a function of the central charge, where we can try to use Virasoro symmetry to extract the answer, but it's a statement about another scale, which has something to do with the Virasoro symmetry per se. And so we don't have that trick up our sleeve. And as evidence of how ADS3 CFT2 is not necessarily a walk in the park, you might ask, okay, so what is known about the space of 2D CFTs with Virasoro symmetry and no extra currents and some irrational central charge, which is to say, a generic 2D CFT. And we have no examples. Okay, so we have 0 examples of explicit controlled CFTs, which are not themselves deformations of rational theories, where as a result of that, the central charge is rational. We don't have any great examples or any examples at all of like deeply irrational, truly irrational 2D CFTs, nor of partition functions with those properties, forgetting about constructing the actual CFT. So partition functions that have a discrete spectrum, that have a unitarity, where the central charge is some irrational number, we don't have any examples of such functions. Okay. And yet we believe that this is the typical theory and that they're all out there. I know Alex mentioned this fact that even in the more constrained setting of looking at theories of self-dual extremal lattices, if you take the central charge to equal 48, there are 10 to the 120 such lattices, and therefore 10 to the 120 modular invariant partition functions of conformal field theories with that value of C. But if someone says, okay, give me a partition function where the central charge is 48.1, we don't have any. Okay, so in some settings, there seem like there are lots of partition functions, but the moment we try to get something typical, we have none. And that's the situation. Okay. So there's a lot to understand. Okay. So we're going to be mostly interested in families of CFTs with large C limits. I want to recall a simple fact that you should just be sure not to think of the central charge as a modulus, the C theorem in 2 dimensions includes the statement that C does not vary as a function of exactly marginal parameters. So you should not think of dialing C and keeping the theory the same while dialing C. When you change C, you change the theory. So when we talk about large central charge, we really mean some family of theories which asymptotes to large C, just like in the sense I was talking about earlier in these lectures. But in 2D, it's especially sharp because C is the C in the C theorem, which is constrained to be constant along fixed lines. So we have in our mind a family of such theories that asymptotes to large C. Maybe there are other scales in the problem, like delta gap, maybe not. And we are interested in CFTs typically with the following properties. So first, positivity or unitarity. So let's see, we have this up here. And in this notation, these D, H comma H bar are the degeneracies. And the statement of positivity is that these are non-negative. Okay. Unitarity is also the statement that also H and H bar are greater than or equal to 0, where the H bar equals 0 state is the ground state. Okay. So no negative dimensions and all degeneracies are positive. That's unitarity. Okay. The second property that we want, and of course, I've already talked about modular invariance, so that one's for sure going to be something we want to impose. Let's impose unitarity as well. We also are typically interested in CFTs that have a discrete spectrum, or otherwise known as compact CFTs. So this means they have a discrete spectrum above a unique ground state. And so in writing the partition function like this, I've written it as a sum. Sometimes you see it written as an integral, in which case the density of state should be viewed as the discrete sum of delta functions. And finally, in a compact CFT, the degeneracies should be counting numbers of states. And so that means they should be integers. So we ask that our partition function respect integrality, which is the statement that not only are these numbers D non-negative, but they are integral. These 3 properties together define a consistent compact CFT partition function. In recent times, we're more willing to consider non-compact or CFTs with continuous parts of their spectra in light of the ensemble discussions. I won't say much about that. Maybe at some point at the end, I'll mention that, although I know this came up earlier in Alex's lectures. But that aside, the traditional question about the space of CFT2s is phrased best as a statement about compact CFTs. Now, a large C let's ask what are the possible spectra that we might hope to get out of something like the modular bootstrap. And in particular, what are the possible optimal or extremal spectra, where the gap has been pushed up as high as we can push it? So what are the choices? What can we imagine? In my mind, there are 4 choices. So the first one, the first one corresponds to what you would call pure gravity. So here I'm assuming that I'm leaning on some notions from Alex's lectures that I've alluded to earlier. Let's not put that there. So we have ground state, and let's put this here. We're looking at the plot. delta, and we're starting from 0, the vacuum. And here is C over 12. And imagine we had a spectrum that looked like this. You have the ground state, and the next primary state is at C over 12, and the remaining primaries are above that. And let me just be explicit. Here we're talking about primary spectra, and just for concreteness, let's assume we're just talking about a CFT with 0 Sorel symmetry. Although this discussion could be extended in situations where you have extra currents to make an extended Taylor algebra. Okay, so this is the sparsest thing that one might imagine that's consistent with expectations from 3D gravity. Right? 3D gravity tells us maybe it is the case that you can have an extremely sparse theory, and C over 12 seems like it's a natural location for the first excited state because that's where the lightest BTZ black hole is. So let's call this the pure gravity option, just the expectation from what we might hope based on what we think we know about pure gravity. The second option is a little less sparse than this, but suppose the first state appeared not at C over 12, but at some order C. So number times C. Maybe a bunch of other states up here. Okay. This isn't pure gravity in the strictest sense, but it's almost pure gravity. The first state appears at order C. In the bulk, this would be some semi-classical geometric state. And on the CFT side, it is a heavy state. So this would be still a striking result if one could establish that such a large gap is possible. Let's call this almost pure gravity. Now, the third natural thing that you might expect to be true if you don't believe that either of these would be true, and so here's C over 12, would be that perhaps there's some states at order C, but there's maybe some sprinkling of states down here, say at order 1 values of the dimension. And they're sporadically distributed. This looks like the kind of vacuum we were talking about yesterday that is scale separated. The order C degrees of freedom come from the ADS3 factor and the black holes and so on, but the sort of sprinkling of these light states would just correspond to some light fields in the bulk, some that don't have asymptotically large growth of degeneracy. There's just a handful of moduli. And just to emphasize that, let me just make it a little sparser down here. And finally, the least sparse option of all, we have the vacuum, we have C over 12, we have some black hole states. And then in the light spectrum, we have some regular spectrum, like a Kaluza-Klein spectrum on a sphere or some other compact manifold. So we really have a lot of light states that really start to pile up as you get toward intermediate energies. So it starts at order 1, but this looks like a KK spectrum. And so this we could call sort of KK or an extra dimensional scenario. Okay. Now, in the supergravity constructions we have, of course, all we can do is option 4, right, as we talked about yesterday. So for example, the ADS3 times S3 times T4 or K3 solution of type 2b supergravity includes this large S3, and so it has a spectrum that looks like this. Right. So in principle, we have examples of type 4, but we don't have any examples of type 1, 2, or 3 on the CFT side explicitly. Okay. And the question that the modular bootstrap tries to answer is, what is even possible? So having laid out the 4 possibilities that seem like they each have some independent kind of motivation from the gravitational side in the order from sparsest to least sparse, let's talk about the modular bootstrap.
Can you give examples of the states that you have in mind, like in 2 and 3? Like what
Sure,
state is
great.
this?
Thanks. Yes. So, so on the gravity side, you mean in gravitational language?
Right, in the gravitational picture, like is it a star?
Yeah.
Like what is it?
good. So let's start here. So in this example, this would be something like a conical defect in ADS3. This is a state that you can think of as putting a particle in the center of global ADS of some mass m and then tuning its mass up until it becomes of order the Planck scale. At that point, it back reacts in the geometry and introduces a conical deficit angle into the geometry. Because the mass is of order Planck scale, that means delta is of order c in the CFT. But if you don't tune it up too much, then you don't form a black hole. So that's the quintessential example of a state that has dimension of order c in the ADS3 context. Over here, I don't mean anything so specific other than just some light, say, scalar field in the bulk with mass order 1. In the
It's like
context of-
minimally coupled to.
Yeah. So the coupling
minimally
is good.
coupled.
Sorry, go ahead.
I just saying minimally coupled scalar, is that?
Yep.
Like,
Yep.
Yeah.
Something
Okay.
that simple where we imagine we have a bulk theory that has a two derivative action and there's some minimally coupled scalar, or perhaps there are some interactions, but it doesn't matter so much for this discussion. All we care about is what the mass would be. And so in some compactification where you have some moduli on some internal manifolds, like Rabiau or something, then you get some light scalars. And here, this scalar in the bulk can have ADS mass, just some order 1. There are also intermediate possibilities where you can have an operator on the CFT side whose dimension scales like root c, and that is not light in the sense I'm using here, but it's not a conical defect because the mass hasn't reached the Planck scale yet. Instead, it's to be thought of just as a kind of heavy probe particle. So whereas a light particle in ADS has a wave function that's spread throughout the bulk, the more you tune its mass up, the more peaked the wave function becomes. And so you can think of a heavy probe particle as moving effectively along a geodesic, but it's not heavy enough to change the geometry. I haven't drawn that possibility just because it's slightly less natural in the sense that c is the kind of order parameter, so to speak. And so order c and order 1 are the two sort of natural possibilities. Any other questions? Okay. So I'm trying to go into a fair amount of detail because I think, well, it sets up the results well to understand what, realistically what one might expect. Okay. So the drive has been, of course, to try to see if this is possible. You want to push up the gap as much as you can. All right. Okay, so back to the modular bootstrap. We said before that the partition function admits a character expansion, which I'll rewrite here. And so the crossing equation of this problem is modular invariance. Right? A simplification that is useful is to look at the S transformation, which is tau goes to -1/tau. Okay, so z of tau equals z of -1/tau. And another simplification is to specify to the spinless case where we set tau bar equal to -tau. Right, so this is the in the Euclidean section, tau bar equals tau star. But if we set tau bar equal to minus tau, then right, these characters, so if we just take a power of q to the h, then this becomes e to the, so q is e to the 2 pi I tau, e to the 2 pi I tau h minus 2 pi I tau bar h bar. But then when tau bar equals minus tau, we get e to the 2 pi I tau delta, where delta equals h plus h bar. So regardless of the spin of a particle, when you set tau bar equal to minus tau, all you're sensitive to is the dimension. That's fine. We can try to constrain the dimensions, but we're just losing some information. And yet another simplification is now useful. Not only should we set tau bar equal to minus tau, but to start out, let's set tau to be pure imaginary. Okay. So then the partition function proceeds in powers of q to the minus 2 pi, e minus 2 pi beta delta. And in particular, we can write c of tau in this language as, so sort of stripping off the eta functions from the characters, and we can imagine we're doing this in terms of primaries, and I'm going to pull out some factor of q to the minus c minus 1 over 24 or over 12. This is essentially a sum over delta of d sub delta e to the minus 2 pi beta delta. And it is important to write the actual factor there. Where here the degeneracy d delta is the sum of all operators of whatever spins with dimension delta. Okay. And let's write this as z of beta. Good. So here's the partition function in this simplified kinematics, and we want to impose the S transformation on it. So what is typically done is the following. So this is how to think about what's going on. Let's define some phi. That's right, phi vac of tau as chi vac of tau minus chi vac of minus 1 over tau. And we'll write some phi delta of tau as the same thing now for the other non-vacuum characters. And the crossing equation, the S invariance, is the statement that phi vac of tau plus sum over delta, strictly positive because we've stripped out the vacuum and we're assuming there's a gap, of d of delta phi of delta of tau equals 0. So we just did crossing and moved everything to one side. Okay. The goal is to use this to constrain the possible deltas. So historically, what happened in Simeon's paper, which is still quite readable, he said, okay, let's expand around tau equals I. Tau equals I is a fixed point of S. So odd derivatives of the partition function evaluated at tau equals I vanish. Viewing the partition function as a function of these d sub delta, you can try to use this to constrain what d is allowed to be by evaluating or insisting upon the vanishing of these derivatives at every odd order. And say working with the first handful, you already get some constraints. And systematizing that problem has been what the past several years have comprised. So the way that people phrase this problem now is the following way. So this was sort of the simple original way and still the nice way to think about it, the sort of more modern functional approach is to find some functional, let's call it omega, which obeys these properties. First, omega acting on phi back is positive. And second, omega acting on phi delta is non-negative for all delta greater than or equal to some delta star. Now, here was our crossing equation. If you can find such a functional, then there must be an operator with dimension less than delta star, because you act on the crossing equation with this functional. The first term is positive by construction, and the second term is non-negative by construction. But you can't get zero that way. So there has to have been an operator of dimension less than delta star. This is exactly the same kind of logic that people use to solve 4-point crossing, and that the sort of numerical approach to that in terms of semi-definite programming, etc., makes use of. And indeed, a lot of the progress in the modular bootstrap came from applying those tools to this slightly different crossing problem. There are some very nice treatments of this in literature. I'll put some references in that document. Of course, besides Simeon's paper, some of the important papers here are a paper by Keller and Friedan, a paper by Collier, Lin and Yin, and then several in the more recent years. There's a nice summary of this technique in a paper by Hartman, Mazach, and Rastelli, and then really just lots of papers that I will give more proper due to in the document. Okay. So this is the idea, and now let's talk about what people find. All right. Any questions before we talk about what people find? Let me make a couple comments then. First, notice that in this simplified kinematics, once we look at the spinless case, where we're expanding in powers of e to the 2 pi I tau, and tau can be complex. Now, if it's anything but pure imaginary, you're going to have phases appearing. And that means that it's a bit harder to utilize positivity of the expansion coefficients. People have tried to do modular bootstrap away from, say, tau equals I. And I think the verdict is still out as to whether, how much can be extracted from that. But all the efficient and powerful results have really come from expanding in the neighborhood of tau equals I would say. Okay, so let's talk about the results. All right, so we had this style plot before. Here's 0. Here's C over 12. Here's C over 6. In this procedure, the central charge is a parameter. And so one can study the solutions as a function of C. It's hard when the central charge becomes large because you're fighting large central charge versus convergence issues. There's a lot I haven't said about how this actually works, but in practice, because this is a sum over in principle an infinite number of operators, indeed, every CFT has an infinite number of operators at sufficiently high dimension. Anyway, you have exponential growth. The algorithm involves truncating the problem in a couple different ways. First, you have the functional you construct, and second, you have the sum. And so you have to try to extend your set of data while at the same time taking the central charge large. So you have these different parameters that are kind of fighting with each other. And in more recent times, there have been some effective methods for doing this, in particular a paper called Fast Conformal Bootstrap and 3D Gravity or something by Hamid, Hartman, and I'm afraid I don't remember the third author, but I think it's Tajdini. Yes, good. So the results here are obtained for the most part numerically and as some extrapolation toward large C. Okay. So C/6 was found to be the gap by Hellerman. Okay, so we showed the optimal gap is at least lower than C/6 in the original paper. So this is already striking. You know, there's a factor of 2 off from what everyone's sort of hoping and wants. Okay. Then there was lots and lots of effort, lots of years going by, some false starts. The state of the art, though, is that C/8.5, this in black, is the best analytic calculation at the present time. That was calculated in one of these papers I mentioned before by Hartman, Mazach, and Rastelli. And the best numeric was in this Fast Conformal Bootstrap paper, where I guess I've run out of space here a little bit. And that, though, is C/9.1. 9.1 should not be viewed as a magic number. I think everyone thinks this is not done, but this is the best result at the moment. So there's more to say, and hopefully we'll be able to say it. And I think there's a bias or desire in the community that this gets pushed down to C/12 somehow. We'd like to prove this, but it's not totally clear whether that actually should even be the optimal gap. I'd say there's not a sharp argument for that. And in some ways, I feel like there are some counter arguments. So
I'm a bit confused by the logic. So we already know that there is a state with C/12, right? So how can the gap be C/8.5? Like,
well, so we don't know that there's a state with C/12 from the CFT point of view. We know that if we trust what classical 3D gravity is telling us, it looks like every 2D CFT should have a state at C/12 in the large C limit. But we don't want to have to trust expectations from 3D gravity. We want to do a rigorous calculation in 2D CFT.
so the result is saying is that we need an operator at C/8.5 or C/9.1, but we don't necessarily need an operator below that.
Correct.
That's what.
Correct.
Okay.
And so we'll see what the future holds, right? So the bound may come down. So in particular, you know you're done when you construct the extremal functional. That is to say, if you have in hand a partition function which has the gap, then you're done, right? So more precisely, if you have a unitary, say, compact integral partition function, that would be a partition function of a CFT that is the type of thing we want. Of course, here we're not imposing all those constraints. We're just imposing positivity and modular invariance. So nevertheless, if you just have a partition function in hand that satisfies those constraints, then you know that you'll never be able to do better. And indeed, that transitions me to my next point. So in fact, Keller and Maloney showed that no bound derived from unitarity plus modularity alone can beat delta equals C-1/12. Okay. More recently, so I said open questions, that this will turn into a question soon. course, this is just fact. Benjamin Collier Maloney found a partition function which seems positive everywhere and is modular invariant, which has delta star equals C over 16 and some large C limit. Okay. So what's wrong with these? Well, nothing from the perspective of unitarity and modularity, but they are both continuous. So the question is, how do we efficiently, or really at all, input discreteness, much less integrality, which is more refined, into modular bootstrap? If we can answer that question, then I think we have a hope of, really nailing the question as we'd really like to see it answered. But this is a hard problem, and so far it hasn't been solved. Okay, so that's one question. I mean, the obvious question, right, is what is the gap? What is the optimal gap? And what is it if you impose discreteness and integrality in particular? We'll see.
This one is continuous above C over 16, right? You have a continuous spectrum above C over 16.
Yes, yes. And again, here I'm talking about spectrum of Virasoro primary operators. Every time I've said spectrum here, it's easy to study the primary partition function. You just strip out the eta function that counts the descendants in a modular invariant way, and then try to impose the modular invariance condition on that thing. Sometimes this is called the primary counting partition function or the reduced partition function. A second question is, what is the spin of this lightest primary state? I think it's often assumed that it's 0. I don't know of a totally rigorous argument for that. Maybe the argument that it's 0 comes from 3D gravity, where the lightest BTZ black hole is scalar, but that's not a great argument. As far as the technique, can the spinning bootstrap help? Recall that we just restricted to kinematics where we are insensitive to spin. And 4, this isn't strictly a CFT question, but can we improve arguments or expectations from the gravity set?
Can I ask a question?
Yes.
So you said, can we use spinning bootstrap to help? My question was, in these best numerical or best analytic results you were talking about, were they doing this with that constraint that you put on? That what it was, H equals or delta is H plus H bar, and we don't have any spin, basically.
Yeah, that's right. So delta equals H plus H bar just as a statement about, well, those are that's just a definition of delta, but the kinematics in tau forced us such that the H and H bar always combine into delta in the exponent, indeed. So they were using this constraint.
Okay.
So yeah, going back up here.
There it is. Yeah, tau bar equals
case here.
Tau.
Yeah. So if you just look at how power in the Q expansion of the partition function behaves when you do that, it just becomes a function of H plus H bar. They were using this, and one would like to do better. There are some papers that use spin, but they don't get the in this setting. They're not approaching the results that I'm talking about.
Okay, so it's not clear if they're not getting to this bound because they're not including operators with spin, or is there any reason to think that having operators with spin would get you closer? Or I guess that's my question.
Yeah. Right. So on general grounds, it's good to use the symmetry in a more general, region of the upper half plane. That's not such, I'm not saying anything so wise there, but I don't think there's a great argument that I know of that it will help a great deal, and maybe that's why not everyone's running to do it. I know that, I mean, people would love to do this. It's a technical issue from how I understand it. But no, I don't think there's any great hope that once spin is incorporated, that will just automatically, C over 12 will pop out without much trouble. And I'm not sure. Yeah, I'm not. There are people who are more in the weeds on the details of this who might have more trustworthy opinions, but I'm not so sure how much that will help.
Okay, thank you.
Sure. Yeah. Thanks. I think actually, I mean, to me, it's not even clear that after imposing compactness and integrality, a gap of order C will be possible. I don't know if the modular bootstrap has enough to answer this question by itself, but I'm not totally sure that the gap should even be order C.
Why is that?
Well, I think a lot of the techniques we have are not sensitive to the fine-grained details of the spectrum, being discrete, for example, and I think that should be important. And I mean, that's kind of notwithstanding the recent progress in ensemble averages, et cetera, where in this averaging of partition functions and over the Narayan moduli space, the average gap is found to be of order C, and that's a beautiful story. But it's the kind of story you want to be able to extend to Virasoro. And Alex talked a bit about this, so I won't go on too much, but we don't really have any idea how to do that. And I think if you start thinking about ways in which, situations in which we know what the spectrum looks like in gravity from a top-down point of view, they look like option 4. So it's very reasonable to say, well, that's just because we need supersymmetry in those situations, and there's extra structure in order to be able to construct the theory reliably in the first place from a top-down point of view. And we should trust the specialness of 3D gravity. But I don't know, I'd like to maybe see a little more evidence there. I just don't know. So we might be missing some ideas that the modular bootstrap needs to be augmented with.
I see. Okay. Thank you.
Yeah, sure. Different people definitely have different opinions. So here you're seeing the fact that I'm the one giving these lectures is coming through here. I think there are some really nice talks about this subject by all sorts of people, and I advise you to sample a wide range of opinions. But yeah, I think it's definitely a fascinating open question. Good. So we've got about 10 plus minutes, and so when I wrote as this final open question here, improve arguments or expectations from the gravity side, that's not unrelated to this first question about compactness, in the sense that the constructions that are either in gravity or motivated by gravity, for example, this one, involve these gadgets like Poincare sums, which always generate continuous spectra. On the other hand, in gravity, now we're teaching ourselves that we shouldn't be so scared of continuous spectra. And so maybe thinking more carefully about the role of ensemble averaging and how it interfaces with the kinds of data we get from the modular bootstrap and related approaches would be helpful in setting expectations. I should also mention that there is a proposal that Alex mentioned briefly, also by Maxfield and Toriachi, for how to do the 3D quantum gravity path integral in a way that would give you a gap of not C/16 as done in this other paper, but basically C/12, but some small shift. And that 3D calculation hasn't been done. They motivated it from a 2D dimensional reduction point of view, but it's kind of an elegant mechanism they're proposing. The thing that remains to do is to actually demonstrate that their proposal gives a modular invariant answer. Okay. So there are many things about 2D CFTs that have relation to the bootstrap. I tried to cover probably the main one. Let me pause and try to figure out how to use these last 10 minutes best. So I'll mention one other thing, and then I'm going to mention a few more questions not related to this modular bootstrap question per se, and just invite questions from you. So other results in the ADS3 CFT2 bootstrap. There are many. Okay, there really are many. So one that should be mentioned here is some work by Hartman, Keller, and Stoika. This is the paper that was alluded to by Alex, which shows that there's an extended regime of validity for the Cardy formula. In so-called sparse CFTs, which have a sufficiently sparse growth of light operators up to the threshold C/12. An extended Cardy means that, well, let's draw it. Now I'm going to draw my delta axis horizontally. The statement is, if in this range, the density of states, delta, is bounded above by e to the 2 pi delta, then the Cardy formula, which normally applies just for asymptotically large delta, applies all the way down to C/12, which is to say, d of delta scales like e to the 2 pi root c delta over 3. So whereas in the average CFT2, Cardy applies way out here, in CFT2s that are sparse, which means this green condition, it applies all the way down to C/12. And that matches the entropy formula for BTZ black holes. The way they discovered this was by sort of playing with modular invariance and large C in a new way. One point to emphasize about this is that this exponential growth condition allows for very fast growth of light states, bounded exponentially, but still very fast and much faster than you would get in a local quantum field theory in d dimensions. So the kind of KK growth that we talk about is of the order e to the constant times delta to some power less than 1. E to the 2 pi delta, this Hagedorn behavior, is more characteristic of a free field theory or the symmetric orbifold theories that are not dual to supergravity. So this kind of universality is really sort of a C-dependent universality. So it's not a statement about strongly coupled theories, because the sparseness condition is pretty lenient, in fact. Nevertheless, it is a condition, it's a bound, and if it applies, then you get this extended regime of the Cardy formula, which is a nice thing. This is one example where there's nice physics that's universal in the Virasoro modular invariance universality and central charge sense, but that's not a statement about delta gap or strong coupling per se. Okay, all those theories behave the same way with respect to this particular result. The second thing I want to mention is that in higher dimensions, we talked about the light cone bootstrap briefly, and the statement that every higher dimensional CFT has this asymptotic large spin sector of essentially free fields, where primaries form composites and look like they form a Fock space. In 2D, there is a similar story. Where instead of just asking what the existence of the identity operator implies for the structure of the large spin spectrum, you have not just the identity operator, but the whole identity module, including the Virasoro descendant of the identity, namely the stress tensor and all its composites. And as I mentioned in response to a question a couple lectures ago, they all have the same twist, which is 0, where here in 2D language, twist is the minimum of H or H bar. So any chiral current has twist 0. And so summing up the full effect of the Virasoro symmetry on this crossing problem gives you a modification of the large spin spectrum of every 2D CFT that nevertheless is very pretty and universal. And this is something that, that I worked on with Scott Collier, Jan Gobet, and Henry Maxfield. And we gave the name Virasoro mean field theory to this asymptotic large spin regime of 2D CFTs, where mean field theory and generalized free fields are interchangeable terms. Okay. This is something that I won't say more about, but I'll put a reference in the document. And there's some nice connections with gravitational thinking there. Okay. So in case it hasn't been clear from my lectures, I think it's just as important to highlight the open questions as highlight the ones that are answered. So I'm going to just end with even more questions that I think are important that are open questions. Okay. Because I want you to leave these lectures with something to do, as if you don't have enough to do already, you're thinking. But these are questions you can think about and try to answer yourselves, and then we can all read about your work. So here are a few. Forget about constructing CFTs, which have Virasoro symmetry and some random value of central charge. Let's just construct modular invariant functions that have these properties. So let's construct discrete, positive, integral, and usually non-holomorphic modular invariant functions that can act as partition functions for C greater than 1 Virasoro CFTs. Just mathematically speaking, if you look around for functions that are not holomorphic, which is to say they depend on Q and Q bar in a way that doesn't factorize, and obey these properties, they don't really exist. They're essentially not understood, certainly not systematically. And if you insist that the spacings between the energy levels is, say, chaotic or sporadic, the kind of thing that we'd want for a generic, strongly coupled CFT, those kinds of functions are very foreign mathematically to the number theorists. And so there's been some nice progress on that, and I only know some of it, I'm sure, but it seems like an open mathematical question just to construct a class of functions that could plausibly even exist as partition functions for the kinds of theories we're interested in. And if that's too strong a statement, then maybe Natalie can correct me in GatherTown, because she may well know this. But to my knowledge, there's not some class of functions out there waiting to be discovered that could act as partition functions in this way. Okay, I think that's an important question. Another one is the following. This is a more sort of physical one. What is the distribution of CFTs in central charge space? I don't know. In higher dimensional CFTs, there are sometimes restrictions on the types of numbers that central charges can be. So, for example, just as a point of reference, in a 4D n equals 1 CFT, the central charges, and indeed all of the protected operator data, are algebraic numbers. So that's not a generic number. In fact, that's pretty restrictive. And in 4D n equals 2, as was only pretty recently shown, A and C are actually actual rational numbers. Even more striking. In 2D, is there something we can say about the distribution of central charges for compact unitary CFTs? I'd love to know the answer. And finally, what is the minimal data needed to specify a CFT? You might ask, for example, about the spectrum. If I specify some of the spectrum, does that determine the rest of the spectrum for me? In holomorphic CFTs, this is true. The power of holomorphic modular functions is such that once you fix all the poles, the degeneracies of the non-polar terms are fixed by modularity. In generic, in particular, non-holomorphic CFTs, such a strong statement is not true, but there should be some statement that's true. In some work that hopefully will be published soon, there's some version of this that I and collaborators have seem to have uncovered, but I'm certainly considering this to be an open question in general. And here you could ask not just about the spectrum, but also about the OP coefficients. And in connection with this, it would be nice to know or to use a manifestly modular invariant formulation of CFTs, in which extracting the other constraints, unitarity, discreteness, etc., is the thing that you do. But from the beginning, you're using modular invariant objects. Again, there's some version of this which seems like it can hold, but and some versions of this which in the context of 4-point functions have been developed. For example, this Polyakov-Mellin bootstrap I mentioned. But it would be nice to explore this more deeply into DCFT. And then maybe these questions of modular invariance can be transformed into questions that can somehow be answered with different techniques. So let me conclude there, and thank you for sticking with it. And I'm happy to take any questions.
Thank you very much, Eric. Let's have some quick questions. Actually, before we have a few quick questions, I just wanted to mention that there's no lecture next. So the next time we'll meet is in Gather at 1:30 local time, and then before the lecture at 2, 5 minutes before that, we're going to take a group picture. So please come to Zoom 5 minutes early and I'll take a picture. Okay. All right. Question. Yes. Himanshu.
I had a quick one. What does the central charges being algebraic number or rational number mean for the CFT or for the gravity? Like you take, so like in 2D, say, I mean, the center charge is related to the G Newton, say. So like, what does it imply for the gravity side?
Yeah, I mean, it implies some kind of, I mean, quantization is not quite the right word, but restriction on the values of G Newton that can be realized in a consistent UV complete theory of 3D gravity. You know, a strong, and in the end, too strong version of this was considered by Ed Witten in his 2007 paper, Three-Dimensional Gravity Revisited, where he explored the idea that 3D gravity might be dual to a holomorphically factorized CFT. And there, the central charge is constrained to take multiples of 24
times.
Okay, so then G, you know, C equals 3L over 2G, and G is likewise constrained to this sequence. What I'm talking about here, or just imagining here, is something, you know, along those lines. I mean, it's not nearly that quantized, but I don't know what the deep answer would be to that question.
That's strange from a string theory
true.
point of view. Is that strange that having G Newton is quantized? Or
I wish I had a good answer to that question. I don't feel like it's that strange, no. But just on the basis that in string theory there are no continuous parameters.
okay, yeah. Thanks.
Yeah, sure. I just want to emphasize I don't have any reason to think that there's something, you know, there's some statement like this must be true about 2D CFT simple charges. And definitely the paucity of explicit examples of 2D CFT should not be taken as some evidence that they're always rational. You know, we're just not nearly good enough for 2D CFT to make that kind of claim.
William?
Yeah. So I had a question going back to trying to input discreteness into the bootstrap. When we talk about these asymptotic density formulas, we're essentially thinking of smearing out over discrete locations of the spectra. And I understand that there's some work being done to formalize this using some pretty complicated Tauberian theorems. Do you have any comments on that, or have you looked into the sort of smearing mechanisms that are sort of swept under the rug when doing the bootstrap like this?
Yeah, thanks for the question. I haven't looked into that stuff myself, but I think that is, so I think that the approach taken in the modular bootstrap and those sorts of questions are a little bit logically disconnected. So the Tauberian methods allow a more precise accounting of the asymptotics, but in the modular bootstrap, the asymptotics aren't really coming into the game in the per se. I mean, actually, what one does is truncates the deltas that one is applying the functional to, and so and then considers this function phi of delta to be essentially a continuous function of delta, which is sort of where you'd want to impose discreteness somehow. But the spectrum is being truncated in that procedure, and so the asymptotics aren't really being used. So I think the two problems are not so far directly related. And I don't know, though, if insights from the Tauberian story could be used as input into these methods. I'm not sure what that would mean exactly, but I haven't thought about these issues deeply. So
Thank you.
Yeah, thanks for the question.
More questions?
Yeah, I have one. When you say a manifestly modular invariant formulation of CFT, would the formulation in terms of tensor categories be the kind of thing you're looking for?
Well, let's see. Maybe you can say a little bit more what you have in mind.
So rational conformal field theories have this description of their global behavior in terms of modular tensor categories. So for non-rational CFTs, there's no general understanding of some structure like that. So is that the kind of formulation of a CFT that you're looking for?
I didn't think of it that way because even there, I mean, it's not knowing that using the technology of modular tensor categories doesn't somehow spit out for you all possible modular invariant partition functions of rational theories, right? I mean, it's not as if that is a fully classified landscape, even. So, you know, what I mean more is I mean, one still has to work to ask what the modular invariants are, given some chiral algebra and C and whatever. And so the MTC stuff can help you with that. So what I mean more is imagining that there's some kind of basis in which you can expand a partition function, and the basis is a basis of modular invariant functions. And then the work comes in translating that basis to the character expansion and demanding things like positivity and discreteness.
Nice.
Now, there's a version of this, which this thing I alluded to earlier, whose application we're thinking about, which is that there's a whole world of harmonic analysis for SL2Z, and in particular, there for square integrable functions on the fundamental domain, there is a basis of modular invariant functions. However, CFT partition functions are not square integrable. If they were, then actually you could, in principle, expand any partition function in this basis. I mean, by definition. And so we're playing around with that, and we have some results, but it is exactly the fact that we want to do this for irrational generic CFTs that makes the problem hard and that makes the harmonic analysis not immediately applicable. In a paper that will come out within a few weeks, I hope we sort of introduce this point and do some things in the context of Arrhenian theories where actually you don't have this problem, because Arrhenian theories are sort of on the boundary of rational and irrational. But I'm hopeful that there's more in the offing with this. But in phrasing this question, I also just wanted to raise it more generally. So you could apply this to partition functions and try to classify or introduce a new way to think about the space of partition functions. But there are other observables in CFTs too that say modular covariant, or so somehow there's more to do than just to think about the partition function. But maybe this technology is useful there. Yeah. And not to mention that even if you can start using it, then you'd want to say, okay, what can I prove with it, right? Can you prove something like the spectral gap, this modular bootstrap bound? I don't know what the answer is to that.
All right, thank you.
More questions?
Yes, hi. Maybe I can ask. So in this fourth scenario that you mentioned, you listed these 4 different spectra.
Yeah.
What kind of restrictions do you have in mind on the growth of the light spectra, and do you assume anything about the spacing? And sort of related to that, is there a relation of this, say the comparison between the 4th and 3rd scenario and this problem of the number of large dimensions that you talked about yesterday?
Yes, exactly. Yeah, that's the distinction I was trying to make. Let me try to make it a little more clearly. So when in option 3, I'm imagining adding a handful of moduli that are light. And so in particular, if I look at the density of states, which I'm going to call rho of delta x is, well, so we're going to look at it in this regime where delta is becoming large, and so it starts to maybe look like this, like effectively continuous. You want to ask, what is the growth of states here? Now, let me do this a little more. So let's look at the growth of light states. So these are states that have dimension much greater than 1, but much less than any other scale, like C or delta gap, say. if we look at the total growth of states, then let's parameterize it as e to the delta to the d minus 1 over d. This is the total growth of states for a perturbative field in capital D dimensions. So here I mean like the primary and all of its composites. So this is the total density of states rho. This is what you'd get if you had, so the first scenario is the KK one. Okay, so let's say we have ADS 3 times S3, for example. In this case, D equals 6. And so you can diagnose from the ADS3 perspective the presence of the extra 3 dimensions by looking at the spectrum in this region here, which is what I tried to draw here. So you don't just have some sporadic set of light fields, you have this asymptotic, which is this exponential growth with some particular exponent. And that exponent encodes the number of space-time dimensions that the fields see. On the other hand, if we look at the scale separated case, then in this case, D would be 1, which is to say it would grow polynomially or just perhaps not at all. Because I'm imagining a scenario where you have a field that has dimension 4, a field that has dimension 22, a field that has dimension 41, and that's it. Something like that. So you just have, some small, very small number of light fields and their composites, and you get some growth that's like D equals 1, or D equals 3 or 2, but not enough to grow you extra dimensions. And so to summarize, the question is a question about how fast it grows here, whether it grows polynomially, exponentially, and if it grows exponentially, then we have some extra dimensions depending on how fast the growth is, and if it grows slower than that, then we don't have extra dimensions.
Right.
Thanks. Did that help? Yeah.
Yeah.
I think in the end that wasn't as clear as I wanted it to be, but I think that was clearer than it was before. So
maybe one follow-up question. So
Yeah.
so if I just assume this spectra, I understand that sort of you can get it by assuming that you take this ADS3 times S3 to start with, that you see the spectra, but can you do it the other way, that you assume this spectra and you see that this number of large dimensions
Yes.
must appear?
Yes, you can. This was the content of a paper I wrote with Fernando Alday. I posted on the Slack actually just yesterday in response to a question Jake had, but yeah, we showed that direction exactly.
Thanks.
Yeah.
Okay, well, we've had lots of questions, so let's thank Eric again for his wonderful series of lectures.